Hello everyone. Uh, in this paper, we will be discussing about the topic parallelism in machine learning. Basically, the machine learning is the application of artificial intelligence where we try our algorithm to learn automatically without being explicitly programmed using previous experience in the form of dataset. Generally, machine learning algorithms are computational heavy and can involve a huge dataset. Traditionally, only single core processor environments were used, which led to the substantial delay in model processing. As the data sizes are increasing dramatically and the number of parameters in modern deep learning algorithms like neural networks is increasing, it is very important that we are able to use parallelism in these machine learning algorithms using multiple processors to optimize model training, etc., which otherwise would take much more time. So machine learning algorithms are generally computational heavy and provide ideal case for using a parallel architecture and parallel programming methods. With evaluation of big data, understanding parallelism strategies and implementing it in our algorithms is very important for extracting maximum possible optimization and saving time and cost dramatically. So, in this paper, we will go through various parallelism paradigms which can be implemented in the machine learning algorithms to optimize model training. Also, we will look at few algorithms and applications of this parallelism paradigms like a priori algorithms, k-means clustering, k-fold cross validation, and MapReduce framework. We will see how these algorithms can be implemented using parallelism techniques, which helps us to optimize and make our model more efficient and more cost and time saving. Parallelism paradigms. With development of deep learning, we have seen increased demand with parallel training. We need to find the ways in which we can use these techniques for parallel training so that we are able to do the model training in much less time. As model and data sets are getting bigger, training time becomes a nightmare with single GPU training. So we can't just use simply a single processor to train our model. In parallelism paradigms, we will look briefly in existing methods to parallelize training. So basically in this paper we will be discussing the two parallelism paradigms. One, data parallelism. The second one, the model parallelism. Also, we can divide the model parallelism in two parts. One, tensor parallelism, and second, pipeline parallelism. Now the first we will talk about data parallelism. Data parallelism is one of the most common form of the parallelism due to its simplicity. In data parallel training, a data set is split into several chunks and each chunk is allocated to a single processor, or this is equivalent to parallelizing the training process along the batch dimension. In data parallelism, we divide a data set into multiple chunks and then single or more chunks is given to a single processor, and then a processor works on that chunk, and then after processing all the chunks the results are merged for the further processing. So each processor holds a full copy of model replica and the and trains on the data set shard allocated. So after the back propagation, model parameters across the processors are synchronized by reducing the gradient of the model. So here in this diagram you can see a data set is there and we are dividing it into across the 4 GPUs, and each GPU has the copy of a full copy of a model and the part of a data set. Next, we will be talking about model parallelism. In data parallel training, each GPU holds a copy of whole model weight. This brings redundancy issue. So another paradigm of parallelism is model parallelism, where model is split and distributed over multiple processors and not the data. So the model here can be too complex with many hidden layers and weights, due to which it is very difficult to fit them into a single node memory. So in this model parallelism, each node is the subset of a model through which data flows. After this, transformations are synchronized with other nodes. The efficiency of this model form using the model parallelism is heavily dependent on how the model is partitioned and how the forward and the backward pass is done using the execution schedule. Next, we can further subdivide the model parallelism into two categories. First one will be the tensor parallelism and the second one will be the pipeline parallelism. In tensor parallelism, we will be uh, talking about how this is done. So, tensor parallelism is an example of intra-layer parallelism where parallel computation takes place within an operation. For example, matrix multiplication will be an example where we can use this intra-layer parallelism. So in this approach, we divide a tensor into several chunks along some specific dimension. So then each chunk is distributed to one of the processor nodes, and after it processing, the result is accumulated using some communication. Consider an example of matrix multiplication of A multiply B, which will result into C matrix, where A and B are matrices of several rows and columns. So what if we can split the B along the column dimension and then distribute it amongst the different nodes? So in this diagram you can see that we have these two matrices A and B. If we divide the B across the column dimension and then distribute it with A in the several chunks, then we can calculate the multiplication of A across each dimension using different nodes. So this is an example of tensor parallelism. Combining these partial results, we will be able to get the correct results. Next, we will be talking about pipeline parallelism, which is an example of interlayer parallelism, unlike the tensor parallelism, which is intralayer parallelism. This approach parallelizes the computation between the layers. So the model is split into several chunks, and these chunks are distributed across the processing nodes. In pipeline parallelism, there are two paths. The forward pass, intermediate activation is passed to the next stage by each node. Then the gradient of the input tensor is passed back to the previous pipeline stage using the backward pass by each node. Using this approach, nodes are able to compute simultaneously and increase the training output. Pipelining is an example which achieves the true parallelization in model parallelism, and it helps in reducing the performance loss due to sequential computation by running the computation on GPU simultaneously on different data samples. So here you can see the figure which is showing this pipeline parallelism. Here we can see the multiple layers and each GPU having the handling the different layers, and we are having a forward pass and the backward pass. So the one of the disadvantage of this pipeline parallelism is that during training some nodes will be engaged in computation which causes stalls and bubble time, leading to the wastage of computation resources. It is similar to what we have learned in our class about pipelining stalling. Next, we will be talking about parallelism in a priori algorithm. This algorithm is very popular in machine learning and used for association rule mining and frequent item set mining. One of the example where a priori algorithm is used is market basket analysis. So several parallel algorithms were designed as an improvement over the basic sequential a priori algorithm, which differs in partitioning and mining methods. These algorithms uses the paradigms which we have discussed previously, namely data parallelism and model parallelism. So let's see the first algorithm type. First will be the count distribution. In the count distribution, we try to keep the processors busy in algorithm even if it means doing the redundant computations. Each process node takes the previous past frequent item sets and then calculate the k frequent item set with its local count. So now we will have the k frequent item set of the local count. Now some of this item will be most frequent globally, but some might not be. So there will be some redundancy across the nodes. The global count is then found using the local count and thus finding global k frequent item set. So the second approach which we can use is data distribution. In data distribution, each processor has a mutually exclusive item set to calculate the frequent item set. So the items in every processor will be having the mutually exclusive items. This approach has a disadvantage that each node will have to broadcast its local result after each pass to other nodes, unlike the count distribution approach, where just the count is broadcasted. So the third approach, which is a candidate distribution. In the candidate distribution approach, each processor generates a unique item set which is independent of other processor while data is replicated selectively. This helps in avoiding the synchronizing steps at the end of each pass. Next, we will be discussing the parallelism in k-means clustering algorithm. K-means clustering algorithm is a very popularly used machine learning algorithm which is an example of unsupervised learning. Unsupervised learning means we have a data set without a labeled outcomes and we have to make the reference on that. So in a simple k-means algorithms, like we can see in the figure that there are many data points and now we choose the k centroids selected randomly and then we calculate the distance iteratively to divide the dataset into the clusters. So in the k-means algorithms we use Euclidean distance, which is a metric which we can use several times. Now the individual distance of data points from the different centroids in an iteration is not dependent on each other. So this distance calculation part in every iteration, if we try to do it, we can do it in the parallel, and this gives us the scope to use the parallelism and optimize the whole algorithm. This algorithm will be efficient if we don't have memory management overhead as a bottleneck for these calculations. So in this figure you can see there's like we have a lot of several data points and we have this k black dots which defines the centroid, and now we calculate the data points distances from the centroids in parallel and then refine our centroids. Next, we will be discussing the k-fold cross validation. It is one of the most commonly used techniques in machine learning for model validation. It involves intensive processing of data segments which do not necessarily need to be sequential. So, in this technique, what we do is we left out one of the kth segment for testing and remaining k-1 segment we use to train the model. This process is repeated k times and a single average integrated model is formed by combining all these individual prediction error results. This way we are able to get average and most general model results. So here in this diagram you can see that a k-fold cross validation coordinator is split into the k-folds, and each k-fold validator is we can distribute it among the different processors, and after the processing we can merge the results and the k-fold cross validation with results combiner. So rather than performing this process sequentially, which could be time consuming when done along with computationally expensive machine learning algorithms, what we can do is we can perform these operations in the parallel. We can process one of the k folds in every processor node parallelly, and then we can combine these results. Next, we will be discussing the parallelism using the MapReduce framework. MapReduce framework is used for parallel computing. In this, programmers get a simple API and do not have to deal with the issues of parallelization, remote execution, data distribution, load balancing, or fault tolerance. In this framework, it is easy for one to use the thousands of processors to process huge amount of data, whether for example it's in terabytes or petabytes. It hides all the complexity. The programmer can run the same code regardless of whether there is a one computer or there are 10 of thousands of that will work on a problem. MapReduce is implemented in a master worker configuration with one master coordinating many workers. A worker may be assigned a role of either a map worker or a reduce worker. So, in a master worker design, there is a master process which coordinates overall activity. It identifies the data, split it up based on the number of available workers, and assign a data segment to each worker. A worker receives the data segment from the master, perform whatever processing is needed on the data, and then sends the result to the master. At the end, master can do whatever final processing like merging is needed to get the resultant data and get back to the user or application that made the initial request. If the bulk of machine learning algorithm work can be expressed as a sum of training sets, using MapReduce works really well in scaling the algorithms for very large data sets. It does so by taking a learning algorithm and expressing it as a computing the sum function over the training dataset. Many of the machine learning algorithms like linear regression, logistic regression, Bayes gradient descent, stochastic gradient descent can be represented in this way. So the MapReduce implements the parallelism by splitting data across the multiple machines, which leads to speed up the model training in machine learning. This figure illustrates the entire MapReduce process. The client library initializes the shards and create the map worker, reduce workers, and a master. Map worker are assigned a shard to the process. If there are more shards than the map workers, then a map worker will be assigned another shard when it is done. Map worker invoke the user's map function key a map function to pass the data and write intermediate key value results onto their local disk. This intermediate data is partitioned into R partitions according to partitioning function. Each of these R are reduce workers contacts all of the map worker and get the set of key value intermediate data that was targeted to its partition. It is then called the user's reduce function, one for each unique key, and give it a list of all the values that were generated for that key. The reduce function writes its final output to the file that the user program can access once MapReduce is completed. MapReduce implementation provides most of the wiring required with parallel processing so that machine learning developer can implement relatively simple functionalities. However, the implementation of MapReduce has some limitations, which makes it less appropriate for some cases. MapReduce is optimized for situations where the key value in its input list is large and can be processed independently. Map function in MapReduce must be commutative to make use of parallelization. To conclude this paper, we say that as data sizes are increasing humongously and new machine learning algorithms like the complex neural networks, deep learning, are we need to get better and more accurate results. It is not only worthwhile but also it's needed to make use of these algorithms parallelly and use the multiple GPU resources which we have in today's machine in order to save computation cost and time. Initially in the paper we discussed how different paradigms of parallelism can be used, like data and model parallelism can be employed to extract parallelism in machine learning. Later, we discussed how few commonly used machine learning techniques and algorithms uses the parallelism to optimize themselves. Also, how we can map use of the map reduce to parallelize machine learning algorithms for very large data sets. As future work, researchers are trying to extract parallelism in the modern complex algorithms like neural networks and new emergent fields like reinforcement learning, as parallelism is very much needed to speed up and make all these computation heavy algorithms viable for very large data sets. Thank you.